Hi guys, welcome to Brit and Joss Explains. I'm Brittany, and today we'll be going over equilibrium. If a reaction is at equilibrium, this means that the rate forward will equal the rate reverse. In order for a reaction to be at equilibrium, it must meet the following requirements. It must be a closed system so nothing escapes or enters the vessel. Change must be reversible, which is why we will be using this arrow in all equilibrium reactions. Color and concentration have to remain constant, and you have to note that it will be a very dynamic process. Whenever you see a reaction at equilibrium, there will be a K. K is our equilibrium constant. So what does K tell you? K will tell you what your reaction prefers, whether it prefers products or reactants. This means whether it prefers to go forward or backward. If K is greater than 1, it will prefer products. If K is less than 1, it will prefer reactants. And if K is 1, it has no preference. This means that concentration of A equals concentration of B. Okay, now how do we get K based on this equation? Well, K will always be your concentration of products over your concentration of reactants. It will be K equals B over concentration of A. Pretty simple. Now, what if I add a coefficient of 2 over here? What will my K be now? Well, K is still products over reactants. However, the coefficients will give you an exponent, just like this. Suppose we have this equation. How do I get Kc? Well, our first step is to make sure that the equation is balanced, because remember, the coefficients are what determines the exponent on top of the concentrations. So in this equation, everything is balanced. Now, our next step is something we haven't talked about yet, the states of matter. This is very important when calculating Kc or Kp. For equilibrium constant calculations, whether Kc or Kp, we are not including solids or liquids. So for this reaction, what is Kc? Kc will equal to the concentration of CO2, and this is it. That is our only product in gas form. The reason solids and liquids are not included in the equilibrium expression is because solids and liquids have both an activity of 1. So in this equation, if we were to count solids, we would add a 1 over here and a 1 over here. However, this wouldn't change anything. So we don't count these in. Let's suppose we have the following reaction. What is my equilibrium constant of this reaction? We know that K equals concentration of products over concentration of reactants. So K equals concentration of NO, concentration of H2O, and let's not forget the coefficients. These are all of our products, and now our reactants. Because right now we are dealing with concentration, to specify, we will call this Kc. The same thing, just K concentration. Kp will be the same thing as Kc, with the only difference being you're using pressures. It will look like this. Products in parentheses instead of brackets over reactants and whatever coefficients you have. Remember, in order to plug in and solve for Kc, we have to have concentrations at equilibrium. If you're trying to convert Kp to Kc or vice versa, you will use this equation of Kp equals Kc times RT delta N, where R is our gas constant, 0.08206 atm per mole Kelvin, and temperature is in Kelvin. Now, this means that Kp will equal Kc when delta N is 0. Delta N refers to the change in moles, or moles product minus moles reactant. So for this equation, our delta N will equal to 10 minus 9, so 1. In this case, Kp will not equal Kc because delta N is not 0 and will not cancel R and T. Now this brings me to my next point. The only thing that will affect K is temperature. Okay, so let's say we have the following reaction. In this reaction, K is greater than 1, which means that products are being favored. However, we don't want to favor products, we want to favor reactants. Now, what is something else that we can do other than change temperature to favor reactants? Here's where Le Chatelier's principle comes into play. Le Chatelier's principle states that we can disturb a system in a way that will help us favor either products or reactants because the system will always return back to equilibrium. Now, what are some ways that we can shift equilibrium? Making an exclamation on equilibrium, not equilibrium constant. We are not talking about K right now. We are talking about the equilibrium system or equilibria with an A. Now, we can change the equilibrium by manipulating concentrations, by changing volume, pressure, by adding a catalyst, or by changing temperature. Remember, the only way we can change K is by changing temperature, which means that all of these have no effect on K. Now, what would happen to this reaction if I increase the concentration of A? Where would the equilibrium shift? Using the principle that we just learned, we know that if we increase concentration of reactants, the system will try to get back to equilibrium, which means that it will favor products. What is most helpful to me is to visualize a seesaw type motion, or where will the ball roll? In this case, increasing concentration on the left side will cause the ball to roll towards products. So yes, the equilibrium will shift towards the right. And if we think about it, adding more reactants can help us get more products. Now, what if we were to lower the concentration of B? Thinking about it in a seesaw perspective, less reactants means less products. And if we place a ball right here, the ball is going to roll to the left, reactants. So remember, when thinking about how concentration will affect a reaction, picture a seesaw. If we increase concentration, a ball will roll this way. If we increase concentration of a product, a ball being placed here will fall towards reactants. Now, the other equilibrium shifts are not as obvious. For example, volume. A change in volume will depend on moles. To visualize this easier, let's change this reaction to this. If I decrease volume in a reaction, I will favor the side with less moles, in this case being C. So I would shift equilibrium to the right. Why does this make sense? Well, if we have a reaction that is reversible, as for this, and they can either have 2 moles or 1 mole, well, if we change the size of the container from here to here, we are very much leaving it no choice but to prefer products because it has 1 mole, meaning that it can be more compact. However, what if we were to increase size or volume of the container? By giving it more space, we are going to be benefiting this side with more moles, in this case reactants. Now it's the same idea with pressure. You have to look at the difference in moles between products and reactants. If we increase pressure, we will favor the side with less moles, in this case products. If we lower pressure, the reactants to be favored because it has more moles. So if the number of moles in a reaction is the same in products and reactants, volume and pressure will affect both sides equally, that it will cause no change in equilibria. So remember, when dealing with volume and pressure, always look at your number of moles in reactants and in the product side. Now, how does temperature affect equilibria? It will depend on whether the reaction is exothermic or endothermic. Now, endothermic reactions want heat. They need heat in order to create products. This means that endothermic reactions plus heat, or when you add temperature, you will cause equilibria to shift right, favoring products, and K will increase. Remember, because K's that are greater than 1 favor products. So it means that the greater the K, the more it will favor products. So this makes sense. Exothermic reactions, on the other hand, when you add heat, you will shift the equilibrium left. This is because they are releasing heat in order to make products. So by adding temperature, you're favoring reactants instead, because it wants to lose heat. So in this case, K will decrease. Remember, only temperature will affect K. In this chapter, you will find something called Q. So what is Q? Q is the same thing as K. The only difference is Q is not at equilibrium. So Q will give you the same expression, products over reactants, but the concentrations that we have will specifically be the concentrations that are not at equilibrium. Well, how will Q help us if it's not at equilibrium? Well, we can compare Q with K to tell us where the reaction will proceed. Here is how to know where the reaction will proceed. If Q is greater than K, the reaction will proceed to the left. If Q is less than K, it will proceed forward. And if Q is equal to K, then we are at equilibrium. Let's think about why this makes sense. Well, we're basically just adding a new letter to help us with Le Chatelier's principle. Because here, if products increase, this will cause Q to be larger than K, because we will have more over here at the top. However, if reactants increase, that means that our Q will decrease because we're dividing products. So Q will decrease and be smaller than K, which, remember, in a reaction, more reactants will yield more products. A ball will roll this way. This is all for part 1, and make sure you check out part 2. Thanks for watching.